Okay, so those who are coming now, welcome again. My name is Seshan Rao. So today what we are going to discuss is binary search tree. Since right now you are already in the trees concepts in the course, so I thought it's a high time right now to start working on the different kind of trees. If so, why BST? Because BST is a the first tree that you should know, and based on top of it, you can build for other type of trees like AVL trees or B trees, B plus trees, all different kind of trees you can build upon if you know the concept of B and BSTs. So we will discuss what is BST, that is binary search tree, and how we can code it in Java, and we will see the operation like insertion, deletion. Okay, that is what we are going to do in this 1 hour session. And if you have any doubts, please type it out in the chat section so that I can see. I have a different device, from there I will look at your chats and then I will try to answer the question. Okay, so let me share my screen first. So I would recommend to whatever questions you are having with respect to session, please type it out in the chat such that I get to know your queries. Okay, so I think it has been started. So let's go to Eclipse. Okay, Eclipse I usually use for uh, uh, writing my Java code. Okay, so what we are going to look at is binary search trees. Let me increase the font. So we will create binary search tree, but apart from that, I will try to tell you an important aspect which people usually don't follow when they program, that is debugging. So while doing this debugging, while creating this binary search tree programs, you will also do some debugging aspect that it might help you while you're doing the programming or coding. That is without running, how you can check that how your program is running. Okay, so that is there. Okay, yeah. So if I have to say binary, so there first is something called as binary trees, and then there is something called as binary search trees. So binary trees are every node will have maximum of 2 parents. In every node will have every node will have max 2 children, and then it can have 1 child also, or it can have no child. So here for 8 is will be called as root. So 3 and 10 will be called their children. So 3 will be called parent of so 8 in this is a parent of 3 and 10. Similarly, 3 is a parent of 1 and 6, and 1 and 6 are children, and the 1 and 6 are also called siblings. So and 1, if you can see, 1 doesn't have any children, so it is also considered as leaf node. So I can just write it as leaf node for better understanding. So similarly 4 and 4, 7, 13, these are called leaf node. Now if you observe 14 is also 14 has only one child, that is 30. So that's a binary tree concept. Now what makes differ a binary search tree from a binary tree is, if you can observe this 3, 1, 6 and 4, 7, these are called left subtrees. They are lesser than the value of 8, that is a root, and 10 and 14 and 13, these are values which are more than 8. So it is called right subtree. So the right subtree is always more than the parent, and the left subtree will always, the values in the left subtree will always be the less than the parent. Okay, so this is a binary search tree, and the advantage of binary search tree is it is mostly used as a data structure. Yeah, since you are learning data structure, this is one of the data structure. It is one of the easy, easy to like, if I have to say, it's kind of easy to make, and it has very good, it is very fast and memory efficient when it comes to operations of insertion and deletion. Okay, not as a whole data structure, but it's memory efficient in terms of their operations. Okay, so that's why you will you have to look at. Okay, my voice is slow. Okay, fine. Now is it clear? If anyone can type it out, it's clear or not. Okay, I will try to keep the this mic in front of my mouth. That will be better. Okay, so yeah, so I so binary tree, it will be a special type. Binary search is special type of binary tree where left subtree will be always less than the parent and right subtree will be more than the parent, and it is very easy to create. It doesn't have that much complexity. It is very fast in terms of insertion deletion, and it's quite memory efficient in terms of operations. So if you know, if you will get to know something of time complexity over the period of time, there its average time complexity is log n. Average is log n. Okay, so this is one important thing, stuff which if you have a cover, I don't think you have covered that in NPTEL course, but you will eventually come going to cover about. So this login is quite fast, and it's another set of topic that we can look at something sometime later as a time complexity. But right now, you just remember that login is quite fast. Okay, okay. So now let's start coding this binary search tree. So we will take this tree itself, that is 8, 3, 10, 1, 6, 14, 4, 7, 30. We will trace and we will try to code. So while coding, if you want, you can code side by side by creating a separate thing, and I will give time for you to take write down the whole thing, or you can take a screenshot for your later reference. Okay, uh, so let's start here. uh, so here what you why since you are using Java, so you should always try to use a concept of multiple classes, and how you can use a different class for operations, different class for creating nodes, and different class for running all those stuff. So it will give a proper segregation, proper readability for your code. That is one thing you should know while writing in Java. So since I have a public class BST, here I am mostly going to use this class for insertion and deletion. I will ask for commands, and I will create separate classes where I will write the functions particular to BST. Okay, so let's start here. Just a minute. Okay, so for creating that, I will create a class. I will name it as BST operations, and I will create a class here. So in this I will we will going to have insertion, deletion, and if possible search also, if we have the proper amount of time. Okay, so search is quite easy, but most interesting would be insertion, and the most complex would be deletion, because you have multiple cases in deletion aspect as well. Okay, so before writing the code, let's understand how you can add a element in the in a binary search tree. So for example, if I have to add 5, I have to add 5 as a number, add 5. So what I have to do is, first I have to check 5 whether it's greater than or less than 8 or not. That is a root. It will always whenever what you're going to do, it's always start with root in binary search tree. Then you will say that okay, 8 is so 5 is less than 8, then you will go to 3. Now you will see that whether 5 is greater than 3 or not. You find it's greater than 3, so then you will go down to 6. Now here in 6 you will see that you see that whether 5 is greater than or less than 6. Since less than 6, it will go to left subtree. So whenever left subtree we are going, it means your value is less, but whenever in going right subtree it's going right, the value is more than the parent. So since its value is less than parent, that is 6, so it is going left. And here again you have a since it's not empty, again you are going to check the 4, and then you will find it out that okay, here I can it's greater than 5, so greater than 4, so I will just write here and I will add 5. Okay, so practically wise, if you can see, you can say that you have to traverse each node, we have to go level by down level one by one, and then you have to see that whether each level it's same, whether it's greater than lesser. So if it is and if it has null, if it has some values empty space or not, like this, like since 4 and 7 is already there, so again you have to go down to one more level. In this one level again you have to check whether that is at 4, you have to again have to check whether it is greater than smaller, and then you have to point it as 5. So that's why you can do. So how we can do programmatically, let's start here. So that is one thing. Another thing is you are creating a operation for BST, but we have to create a separate identity which is called as node. So we will write at we will create a node, a class, which object we will going to use uh, while creating a BST. So there are three aspects of a in every node there are three aspects. So suppose 8 is there, so it has three aspects. So what three aspects are? 8 in the 8 as a root, it has root as its own value, that is data. The data is it has 8, and then it will have something called as left. It will have left child, and it will have right child. Okay, so that means it will have left child or it will have right child. One will also in this case one will also have this value of one left and right, but this right now it is considered as null if you see the BST here. So considering that, we will keep these three values always during the BST. Okay, now that now we have created a node which is an object that whenever we are going to use create any we have to add nodes in the tree, right? So whenever we're going to add something, first we have to create a node class object, and then we are going to add that in a tree. Okay, so first we will go with so just usually we go by logic wise. What we're going to do is we create an object for BST operation, and I will create new BST operations. So I created a new object called A, and then using this A, I'm going to call all the functions. Another thing that I have to create is something called root, because everything whenever you're going to enter a binary search tree, you have to start only with root. So I am going to create a root object in the node, and I am going to pass it value as null, because right now we don't know what value it will have. Okay, so and for the so that is there, and then I have to use certain things such that I have to use something called a insert, and I have to add suppose 8. Okay, and I have to pass root as a node, and I have to in the root node I have to pass it as 8 value. So to do that I have to create an insert function. So let's go here in BST operation and create a public class. So public class will be there, and then say public function, public method name insert, and I am giving the I am returning the value as node itself. So whenever I'm adding something, it will directly come down as a node object, and that I will pass I will receive node as a node as a parameter, and whatever the value that I'm going to insert right now. Okay, so this is done. Now first aspect always you have to check is whether node is equal to null or not, whether it's an empty tree or something you have to create a new node or not. That is always you have to check, and once if it is empty, then you have to create a new node. So I will create new node, and I'm going to pass this particular value. So right now, since BST is empty, I'm going to pass this value as 8 here, and then I'm going to create. So I have to write another function. So here I will write again a public method with node, and I will say create new node, and I'm going to take only value as some value here. So let's say it as, okay, let's take n value. Okay, and then I will create a object of node, because node is something we always need, a new object of node, and I'm initializing it, and in that a dot data, since we can see that in the line 19 to 20 we need to fill all these three values, data, left and right. So for a dot data, that is the new node, we have to we have to assign the value of n. A dot left, since we don't have any other more data, so we will give it as null and null. So since we are creating new node all the time, we will pass the value as null. Okay, and since we are passing a node variable as a returning value, so we will return a value. Okay, so till now, so what we have created is we started with BST operation. We thought where we're going to define all the functions, and then we have created a root node object for the class node. Node is a core component in a BST. So everything which we're going to add or delete something, we will call in terms of node. So that, and I have to insert some root value. So till now everything is perfectly okay, and we can start running here. So here something we will do more and more, but here I want to show you something, that is something called debugging. So we are not printing anything, so without printing also can we see what is the status of a particular code or not? That is what we need to see. So for that we need to look at debugging. So I can say for Eclipse, but similar process can be done for other kind of IDs like Visual Code or IntelliJ. So the process will be almost similar, but the function, the keys and the options will be, or with name, be different. So I wanted to observe this part, and we will use this debugging over and over in this upcoming time. But I want to start with that. So right now we have created a node. So how we can check whether this node has been created or not? And we are returning a node all time, we have to pass it, we have to store it in a root variable. Okay, so to have a debugging point, you have to create a breakpoint. To create a breakpoint in Eclipse, you can directly click this, like in this line number 48. I am in the line number 48. Okay, little bit, yeah, I am in line number 48. So I just have to double click here. I will create a breakpoint. If you can see a little closely, it's a blue dot is there. Okay, that is one aspect. So what will happen is, when I debug, it will debug all the code, but it will stop at this line. Okay, then if you can see my cursor above the top, the top of the screen, in the Eclipse there's something called as debug, that is a bug shape will be there. So if I click there, debug, so it is starting, debugging has been started. So this dialog box will come. That is something we don't need to know right now. Let's focus on here. But you can see that the debugging point, the breakpoint, it is kept as green. Okay, so this is how here the program has been stopped. So what we have to do is, we have to see step by step how the function is progressing. So what we will do is, okay, if you can see again the top, there will be a red button on the left hand side of the screen, terminate, and beside that there are two buttons will be there. I know you cannot see that, but it's written as step into and step over. Okay, so right now here, root equal to a dot insert, we are calling an insert function. So we will click on step into. So if we do step into, so it is going on insert function. I think now you can see that the green line has been highlighted over line number 35. Okay, so it went there. Now to go to the next from line number 35 to go to the next line, there's a cursor called step over. So if we click on step over, so right now it is seeing that node, right now node value would be null because since we don't have any data. So if we go step over, so it satisfies this node equal to null, so that's why it went to return create new node. Now create new node is again a new function where we are passing a value, that is 8 in this case. So when we will step into this debugging part, we'll go to the function called create new node at line number 26. The green line has been highlighted. I'm using Eclipse as an IDE. So right now you try to understand this debugging from here, then similar approach you can use for other different kind of IDEs such as Visual Studios, IntelliJ and others. Okay, so here line number 26, from line 36 to line 26 went here, and here we are creating a new node named A by creating an object. So if I step over, so it is assigning the value n, that is 8 in this case. So if you can, okay, so if I highlight here and because some slow, we can see that the n value here is 8, that is we have passed in the main function. After that is a data and a left and right, it will go and it will assign the value and it will return the a object. It will return the a object here, that is it will return here, and if we go there, so it will come back and returns the value that is called root equal to root /8. So if I click on root here, that is the returning value. Okay, why it's not getting, okay, so if I do like this, till now it's not there because we're still at the breakpoint. If we step over again, yeah, now if I do again, yeah, so here if I clicking on this, so what I read it out, what it say that it assign a node ID equal to 25, that for the node, and that root data value is 8, left is null, right is null. Okay, so that's how we have created a one root node value. Okay, similarly we are going to do for others as well. Okay, so this is the debugging we are going to do. We will see more debugging thing here when we write more code. So I will terminate the debugging right now. If you don't, it's still okay. We'll again go through this debugging process that by creating breakpoints and see how actually the work is going. So right now new root has been created. Now since everything is going through root and we have to add new nodes, so we have to start with root only and then we have to add values. So considering this what you say, okay, considering this binary search tree that we have considered earlier, we are going to use this same thing to add in our binary tree. So I will write it down for my reference purpose. So it will have 3, 8, 3, 6, 10, 4, 7, 1, 14, 13. Okay, so in this order we will try to add it and we will see how it will go. Now to add 3, now since we have, if the node is null, it's still okay, but now when we add 3 and we have to go via root, the root node will be not null, so we have to add further conditions here. So further conditions would be if val is less than node dot data. So since every time we pass root as a starting point, so we will see whether the value is less than the root value or not. If it is less, then we'll go to the left side of the node and then we will recursively call a function called node dot left and we'll pass the value. Okay, else if we have to have anything else, that means if value is greater than node dot data, so I will go to right side of the node I will see the right subtree, and there I try to insert node dot right. I will give that node right value, and then I will pass the value, whatever the value I'm going to add. So in this case, when we are going to pass 3 here, so it will start with 8. It will say that okay, 3 value is less than node dot data. In this case would be 8. So it will create a separate node in the left side of the 8. So like here, it create a separate node here, and then it will add the value. Okay, now so I think we are almost done. So if the value is greater than node to data, we will insert right, and we create a right node, and then we will add that value, and then we will just return the node. Okay, so I think this is all is needed for insertion. Okay, no more other. So we just have to check whether node is null. If null, to create a new node. Okay, if the node is when you add a new node, then you have to check that whether the current value is greater than less than their parents. If it is less than parent, then go left. If you more than parent, go right, and then at the end you return the node. Okay, this is much we needed. And by creating a new node, you just create a new object called a, and there you just add this values n for a dot data, and left and right you keep it as null. Okay, so now if we have to copy paste and add the values, let's insert the values. I will just change. I will copy paste in command and just change the values here. 4 7 1 14 and then 30. Okay, so we just have to do this right now let's see how the functioning of function will work via debugging. Using debugging, we will see that. So what I will do, I will stop at 10. That will be better, because we will be creating a right subtree. So at line 56 I'm creating a breakpoint. So by that time, ideally it should have add 8 3 6 in the binary tree, and then 10 he has to create a right subtree of the root node. Okay, so let's start it here. I will click on debug, and its debug is it's a bug symbol which is given in the Eclipse that you can find at the top of the toolbar. If you click on debug, it is starting. Okay, so right now we have created till now we have BST of 836, and we are going to insert 10. So if you understand how I know that it has already been created, I will create link on root. I will click on this. Okay, I think my computer is slow. Let's see. Yeah, okay, so unfortunately I can't increase the font here for this inbox, but I will read you now here what is there. So at root node data is 8. Okay, at left if I increase, so there will be data called 3. That is here 8 and 3 is already present, and then we are going, since we added 6 also, so in the left of data, so right of data, we have 6 also we have added. Okay, so by this time 8 3 and 6 is already been created. Now we have to see the 10. So if I click on this root variable, that object, in right, I clicked on right the root of right, it is still null. That means when since 10 value is greater than 8, it will go and attach to the right side of the root value. So we will see how it is happening. So we will go, and there's two functions called step into and step over. So I will go click on step into, so that will go to the insert function. So now it is going to the insert function and checking whether node is equal to null or not, which is generally is not the case because we have passed the root value. So it will check that line number 37, that is whether the value that we have passed in this case is 10. Okay, I will check. It's better if I show it here. So here the val is 10, so we are going to use everything as val. Okay, then we are going to see whether val that is 10 is less than node data or not. Here the node data is usually is 8 at the starting point. Okay, so then it is failed because 10 is greater than node the 8. So it will go, and then it will go to line number 40, where that we try to insert at the right side of the tree. So if we go there, since again a function, so it's a recursive function, so again we'll go and step into, so again as a recursive function it will go at the right side tree and see that whether node equal to null or not. In this case it is true. We don't have any node which is at the right side of the 8, so it will create a new node. So if we step into here, so we will get a node, so we have to create new node here. Now in that new node we will put the data called 10. If I have to see, just a minute. So right now the value is 10 for creating a node for 10 value. Then we keep left and right as null. Then we'll go debug the next line. It is all perfectly fine, and then it returns the value a. That is it creates a node of 10 and it is returning, and so it will return here create new node 10. And then if we go again, since it is recursive, it is go back to the back condition. It will come down to one upper layer of the function, and it is going to return the node value. So if we click on the node value, so node is 8. Now earlier the right was null, but now the data we have added is 10, so it created successfully this 10 value in this BST. Okay, so after this let's step into, okay, so now it has created for root 10. Similarly, if we step over, it will create, so it's already created for 10, it will create for 4, 7, 1, 14. Okay, let's go for 14. So we have created 10. So by this time, if you have to see, by this time only 14 and 13 are remaining. All these things, that is 8, 3, 10, 1, 6, 4, 7 are already been added. So how you can check that it has been added or not? You click on the upper line number 55 root, we check, and since the left subtree is completed, so I will check mostly left nodes. So in left nodes I will check that 3 is present, 3 left is 1, and 3 right is 6. 3 left is 1 and 3 right is 6. Okay, and then I will see for 6 left will be 4 and 6 right will be 7. Okay, so here, okay, but we are interested in 14. To add 14, so we have to see that date. So it has right node which with data 10, and then we left has null, right has null. Since 14 is greater than 10, so it will ideally go at the right hand side. So if we step over here according to the code and check the root again, okay, so if we go here, since 14 is greater, we come to right node with value 10, and then again left value is still null, but right node has been just created, and then in which the data has been 14. So that means the 14 has been added. Similarly, 13 will be added as a left child of 14. So this is how we are going to, we have inserted the we have created and inserted the BST. Okay, now what we are going to see is a little tricky operation which is called deletion. So what is going to happen here is, let's add, so if I have to use here also, I will just write it as root, I will write a dot delete and I will just pass the value root, and I will give the value, for now, for namesake I will just give 1. So we will see how it will work. Now deletion in BST is little tricky, okay, because it has 3 conditions. Okay, first let me create a public method for that. So node delete, and I'll have node in var. Okay, so I have created a delete method, and I have to write the code, but it first we should know 3 condition here. So what 3 condition we will see from this here. Okay, so if I delete any leaf node directly, that is in this case leaf node are 1, 4, 7, 13. If I directly delete them because they don't have child, I can directly delete them. So I don't need to think much about it. But if I delete 14, I have one child here. So what I have to do in this case is I have to put 13 in. I will delete 13 and will keep in place of 14. That means if I'm deleting 14, so I'll just put 13 in this case, and I will remove this. Okay, so that is how for one child we have to think. Okay, let's keep back the original 13. Okay, now this is another case. Third case will be when a node has 2 children, that is 6. Suppose 6 is there or 3 is there. Okay, then how I'm going to choose which element to I will delete this element 3, that's fine, but which element should replace, because it's middle node, right? So I should look out for something called as in order successor. Okay, so I will discuss more about in order successor when I'm going to write the code. Okay, let's quickly write the code here. So I will just write conditions. First condition, deleting node with no child. Okay, deleting node with if it has one child, and deleting a node with 2 child. Or here we are going to have in order successor. I will discuss more upon in order successor when we reach to that point. Okay, let's start coding here. Okay, so first we every time we have to check whether the node is empty or not, whether I'm trying to delete an empty tree or not. That is first thing we have to check usually. So I will just put it, that's the case, I will just return null. If node is empty, I will just return null. That is one case. Now another thing that I have to see is, suppose I have to delete here 6, but to delete 6 I have to reach till 6, right? So I have to search that whether 6 is less than or greater than 8. Then I have to search, okay, since less than 8, then again I have to search whether 6 is greater than less than 3. So I have to write that code as well, just like how insert we have done. So in that case I have to write the val, and val is, if val is greater than less than the node of data, that is if the value that we are the node that we are going to find and delete, if it's less than or greater than parent. So in this case less than parent, I will recursively call the left child, and I recursively call the delete function keeping left child in mind, because at that point of time I don't have to look off other aspect. So if I want to delete 6 here, I don't need to care about 10, 14, 13. So my tree became half by that time only. So I'm looking only at the half of the tree. Okay, so same goes for if I write I have to see that if the value is greater than the parent, I'll just write node dot write. I will recursively call the function node, keeping node dot write as a parameter, and value, whatever the value that we are going to delete, because that is something we need to search. Okay, this is there. Now comes down to if both these conditions are not for, means I found the node wherever it is going to delete. Now I have to search for three. Now I have to search for these three conditions, that is deleting whether the node has child, whether the node has no child, or how many childs are there. So that is something I need to look at. So if I start with, I will check directly that if these two conditions are, so it will accept that the value is actually equal to node of data. So I am checking right now only the child values, whether it has child or not. So I will just check that whether node dot left is equal to null, or node dot right is equal to null. So here I am checking condition for test condition for no child and one child. So I am just checking the case for no child or one child. Case for node with no child or one child. I am keeping both this condition together. So if I have this, so either both are true or both are false. So sorry, if any one of the two, we will go inside, and then I will create a temporary variable with temp name, and I'm giving some value for temporary object temp with, I'm giving null value here to store the data basically. Then what we are going to do is temp dot node left, we will check that which part is null actually. Okay, so suppose if the left side is null, okay, then I will go to node dot right. Otherwise, if the left side node left is not null, then I will go node dot left. Okay, so now what I am done is, it's called tertiary conditional operator. Okay, so here I am checking that I have to assign some values to temp. So what I am checking whether it has any left or right side value or not. So considering it might have one child, so I am checking that whether the node left value is null or not. If it is actually correct, then left node is actually null, that is no child. Then I will select the node dot right. That is, it's kind of if else but written in a single line. Okay, then node dot otherwise if the node dot left is not equal to null, then I will select node dot left as it is. That is, it will be else part, and node dot right will be the if the condition satisfied. Okay, now this thing I have done. Now again I have to check the condition. Now since if suppose the left node is empty but right node can also be empty, right, because we didn't choose AND operator, we use OR operator here. So again we are going to check whether this temp object that we have selected is equal to null or not. Okay, if it is not equal to null, I just have to return null, that's it. Okay, so I will tell what is happening here, and then if the node has at least one child, so what I will going to pass that value, that is one temp. Okay, so to give a little bit demonstration here to understand what is happening, what we have done in this 4-5 lines of code is for 1 or 0 child. So we are checking that once I get the value, so suppose I am going to delete 1 here. Okay, so if I am going to delete 1, so I am going to see that whether it is have any child or not. So but I am keep also checking for one child. So I wrote this condition of whether the left child can be null or right child can be null. Both can be null also, but still the condition satisfied. Okay, to know that whether left child is null or not, if left child is null, there is a high possibility that right child may have value. So I assign node dot right to temp value. But again I am checking that whether this temp value has null or not. That means it has if node right is also null, then I will return this value as null. But if the row dot right has some value, it will return that value. So what it means is, here if since no child is there, I will return null value. So eventually in the delete phase it will remove 1, but in the case of 14 it will not happen like this. It will see the okay 13 as a left child I have, so it will return 13 and it will keep in place of 14, and then it will delete 13. Okay, we will see when we will do in the debugging part. Okay, so this is for uh, if checking the case for if the node has 1 or 0 child. Now checking the case for node with 2 child. Okay, here I have to see for in order something called as in order successors. So for that, just let me write the condition first. So this is the if that we have written. Now else is for 2 child. So I have to write as I have to find who is the successor which can replace the deleted node, and for that I have to create a function get successor node. Okay, before going there, let's discuss what is successor. Okay, so there's something called as in order, pre-order and post order in a BST. In order, post order and pre-order in a BST, in a way that how you can represent the BST in an array. For that, so if you do in order, the specialty of in order is it will give you sorted array value. So if I write it down properly in an array, it will start with 1 3 4 6 7 8 13 14. So it will give me a sorted array if I do a in order of a BST. Now what is in order successor is, when I'm deleting an element, I should also maintain the balance, how the BST look like. Okay, if I replace 3 from 6 here, it will give a different it will instabilize the BST. So what I mean is, if I replace directly by 3 by 6, okay, then ideally I have to change 4 from here, and I have to keep that in the left hand side, and then since it left and 1 is less than 4, so if I do like this, I have to keep like this, and again I have to see where the 1 have to come. So 1, since it is okay, since 1 is less than 1, I have to do like this, and then here I just need to put 7. Okay, so I have to change a lot of nodes just to put 6 in place of 3. Okay, so but if I have to reduce this computation, I don't want so much of complexity, I will use in order successor. That means I should select a variable which is next larger than the deleted element. Okay, so in this again come back to now again back to here. If I have to delete 3, I need to find a value which is greater than 3 and comes in next in line when you sort, if you put this BST in a sorted array. So after 3, the next biggest element is 4. So what I have to do is I have to take this 4 and then put in this place, and then I just need to remove this. So just by putting 4 up there, I'm only removing one node, that is 4, from the tree. I'm replacing 3 by 4. That's the only computation I have to do. But if I have to change 6, I have to do at least 3. I have to do 3 nodes, and I have to arrange nodes separately. So a lot of computation is happening in the background. To easify, we are using in order successor. So if I have to delete 3, I have to put 4 here, and still the BST is still valid without changing any other nodes. So we are going to use that thing. So first I have to find that okay, if I have to delete 3, I have to find who is the successor who is going to replace 3. So for that I have to create another function called successor. So let's create a successor value first. Find successor function. So to do that, I will write public node get successor okay, and I'm going to pass the node value, because for that node only we have to find a successor. Okay, first I'm going to check if the node value is null or not. That's a typical thing that we have to do every time. and then if the value is actually null, then return null. Otherwise, if you look logically in this BST, and 4, yeah, if you look logically in the BST, after 3 I have to find the leftmost node of the right subtree. That is something I need to find. So what I have to do is I will create a temporary variable which stores the right subtree or the parent of right subtree, that is node dot right I will do, and then I will create a while loop to find the leftmost element of the right subtree. Okay, so this temp dot left is unless and until it's not equal to null, I will keep on go left and I will just change the value of temp dot left, and then I just return the temp value. That's it. Okay. Okay. Okay, so by this time what we are doing here is we are finding a get successor and we are finding in order successor. So what we are doing is, if I have to delete 3, I have to find the in order successor. That means I have to check for this right subtree, that is 6, 4 and 7, this right subtree, and in this I need to find the leftmost element tree, that is 4. So once I found it, I will pass it here in successor, and I just need to store it in another variable. So I will keep this node dot data. I will replace the 3 with the successor value, and node dot right. I'll just, and then I will go to node dot right, because from there itself, from the right subtree itself, I am taking those value and then I am finding that particular value. So in this case, node dot right and the successor dot data. Okay, if I do like this, and I'll just return node. Okay. Let's copy paste here. Okay, this is, I think, is done. Delete, wait, it's coming. Oh, okay. Okay, we will do debugging to get to know what we have done, but to again tell what I have done for 2 child is, we have find a in order successor through this function, where I'm going to the leftmost, finding leftmost child of the right subtree and then passing them, and I'm replacing that value with the, so that means I'm finding 4 here, and then replacing 3 by 4, and then I'm ordering for delete operation for the 4 in this case, that is the successor data. Okay, so let's see how it will work. So for that, okay, let's start with the normal thing, root. Okay, so I will write it out. So we will call for operation of root. I think, let's see, okay, something is still array. Return statement must be okay. Return statement must be void. Return the node. Okay. Else, okay, I just need to add run node. I think now it's perfectly fine. Okay, so let's start with the I will do the debugging now. Let's see how. So we will going to delete 1 here. So if I have to see 1 has with no child, so let's delete 1 and let's see how it is going to happen. So to do that, I will create a debug point here at the line 116. I will use the debug symbol in the Eclipse. I will run it, Okay, it started. Okay, let's see. Oh, okay, so I think I have to remove this sticker point. Let's go. Yeah, yeah. Okay, yeah, so if you can see the green highlighted line, this is where we have to see 1. So that 1 right now in our current BST tree is with no child. So let's go in delete operation. So we went to the delete operation, and first we are checking whether node is null or not. In this case the node is not null, so we will go check that whether the node that is the root here, in this case if you see the value, right now the node is root. So from here it is checking that whether the value in this case would be 1. Okay, why it's not showing. Yeah, so here we are checking 1, we have to delete 1. So it is checking that whether 1 is less than 8 or not. Obviously it is less than 8, though it will go for left. Then again it will cause recursively the delete operation. Oh, it is not going. Interesting. Oh, okay, I did a mistake. Okay, just a minute, I will start again. Let's start one more time. Can we write the same code on the command prompt? You can try it out. For that, different compilers are there, but right now as far as know, I can't give an exact answer. Command prompt you can write. You have a something called vim editor, and different kind of editors you are there in command prompt which you can use to write the code. Okay, so let's go here. Okay, I'm going here. Okay, so if I'm going in delete, again I have to go into delete. Again it's checking whether it's null or not. It is checking whether the val is in this case the node value here would be 3. So here the node value will be 3, so it comes down to 1 down level. So again it is checking whether it's 1 is greater than or less than 3 or not. So it is less than, so it will again call the delete function, and here the node value will become 1. Okay, so here the node, it comes down to node value, so we reach the actual point. Now what it has to see, it will check the if and else if condition, it is less than or equal to data. So this if and else if condition will not fall into place, so it will go to check else part. Now it will first check whether it has child or no child. So it is here node dot left and node dot right, both are null. If you have to see, we can check it again. Okay, so for node 1, left is null, right is null, both are null. Since both are null, this condition will satisfy, and it will create a temporary variable, and again it will check that whether load of left is null, which is true in this case. So it will assign temp as a node dot right. Now in this temp the value will be null. Okay, let's see whether let's go to another point. Okay, so here since the temp value is also null, temp value is equal to null, that is correct, so it is returning null value. So when it's returned null value, so it is going here, so node dot left will become null. So in this case right now if you see data is 3, data is still 1, so again we have to pass one more value. We have to do one more step, return node. Now if you see the node here, now data was 3 and left, now earlier it was 1, now it become null. So that means here 3 was there and 1 was there. Since we have found that there was no child, we directly passed the null value here, and then it has deleted the 1. So now it shows 0, nothing there. Okay, so this is for 1, that is working perfectly fine. Now we will look for 2 child. Same it will go for here also, but in this case it will pass this 13 value to 14. and it will replace this value, and it will here in the left and left child of 13 it will give us null value. Okay, so this is there for one child deletion. Now we will do for two child directly. Now that means we try to delete 3, and we see that whether this 4 will replace 3 or not, and then we will see and then we have to remove 4 from here as well. Okay, so let's go here, and then in the main function I'll just I'm keeping all this binary tree as it is, BST as it is, and then I'm just going to remove 3. Okay, let's start one more time debugging. So our binary tree has been created. Now we're going to delete 3 from here, and let's go. Okay, so we are going to check whether node is null or not. Here in this case the node is 8, that is root. So let's go here. So 3 is less than 8, that is perfectly fine. So it is going, now it is again recursively calling node.left. So once it call node.left, here the node will become 3. Here the node will become 3. So now again it will go and check whether 3 is less than or greater than node.data, but these condition will fall, and then it will check here for the 0 or no child case whether left node or right node are null or not. So as we can see here, the left node and right node are both are filled by 1 and 6. So what it will do is, okay, from line 61 it will go to else condition directly. Now here it will try to find the successor of the node. That means he understood that it has 2 child. So if we go here, so it will go into, that is, it comes down to line number 84, that is, and then it's checking whether node is null or not, and then it is trying to find a successor using this while loop. That is, it's trying to find the leftmost node of the right subtree. So after finding this, it is returning the temp value. So if you find the temp value node, the data is 4. So it is correctly identify that the 4 value. That means you identify the 4 value that we are going to, and it is going to pass it, and then it's going to replace it. So let's see what will happen now. After this, okay, so from here I got in successor node, I got a 4 node with 4 value, and then I'm going to erase 3. I'm going to erase it 3 and put the 4 here, and then again I'm going to call the delete to delete 4. So if I have to see node again, see, now since we have we erase 3 and put 4, but again we have 4 node in the tree as it is. So since if we erase 3 here and put 4, but I have to remove this 4 from here, so that's why we are calling this line number 76 to again delete this 4 node. Okay, so I am putting successor data, that is 4, and I am going to see that in the right subtree I need to get this 4 data. Okay, so if I do this, okay, I skipped the step there, and I'm returning the node. So if I'm returning the node, let's see how it will. So okay, data is 1. Okay, so let's see. So since I have deleted 4 here, the same process that we discussed earlier. So ideally it should look like this. The left subtree should have 1, right subtree should have 6 and 7. So, and it's going to return that. So here in this aspect, so we have node 4, and then if you go to left side, we will see that 1 is there, and if you go to right side, we can see that the right side has 6, and then we will see the left side is null, which is expected, and the right side will have 7. So it is working perfectly fine. So that means it is checking the 4, and then go to right side, it will say 6, and then it will see that 7 is there. So let's complete this this value, and then it is returning node. So that's how a deletion is happening in a BST. Okay, so I think we have already passed 7, so let's end this session today. Searching is quite easy, same like what we are doing here in this code, right? We check whether we will take the value and then check that whether it's greater than, less than its parent or not, and then if these conditions not fine, then it will check whether the value is equal to no. That's a simple code that we can write uh, for the search operation. Okay, so today what we have discussed binary tree, binary search tree, and its basic operations, that is insertion and deletion, and we have seen it's how the value changes through debugging, through breaking points and debugging, which I feel or everyone should try it out in your system. Okay, so a question is, can you please share the code link for this session? Yes. So the code will be shared by NPTEL as well. Uh, Once I stop this recording, I will share you the YouTube channel where I'm going to upload this video. There, the link of the code will be there, which you can use. Okay, so